Good morning. In this talk, I will present our work entitled A Fractal Laplace Transform. The main goal is to construct a Laplace type transform adapted to a two-parameter fractal derivative. The parameters are alpha and beta. One of them modifies the scale of the independent variable, and the other modifies the response of the function. I will focus on the main ideas behind the construction, the operational rules, and one application to a radial heat conduction model. We begin with the derivative. The classical derivative compares the change of the function with the change of the variable. In the fractal version, this comparison is modified on both sides. The parameter alpha changes the scale of the independent variable. The parameter beta changes the scale of the function values. So the numerator is built from f raised to beta, and the denominator is built from x raised to alpha. We use the signed power convention. This allows the expression to be treated consistently on both sides of the origin. There are three basic points to keep in mind. First, when alpha and beta are equal to 1, the classical derivative is recovered. Second, when beta is different from 1, the operator becomes nonlinear. And third, the same derivative can be interpreted as an alpha scale derivative applied to f raised to beta. Now we look at a concrete example. The function is shown in the upper graph and its fractal derivative is shown in the lower graph. The important feature is that the function has two delicate points, one at x equals 0 and another one at x equals 2. When alpha and beta are both equal to 1, the derivative behaves like the classical derivative. In this case, the lower graph shows singular behavior at those special points. Now we change the parameters. First, alpha is decreased. Notice that this affects the behavior near the origin. For this example, when alpha is below the threshold 2/3, the singularity at x equals 0 is removed. Then beta is increased. This affects the behavior near x equals 2. When beta is larger than 2, the second singularity is also removed. So the parameters are not only changing the shape of the graph, they are changing the regularity of the derivative. This is one of the reasons why the definition is useful. It gives a controlled way to modify singular behavior through the parameters alpha and beta. Now we move from the derivative to the main motivation. The Laplace transform is a crucial tool in analysis, especially in the study of differential equations. One of its strengths is that it converts derivatives into simpler expressions involving the transform parameter and initial values. This is what makes the classical formula so useful. So once we introduce a fractal derivative, it is natural to ask whether there is a Laplace type transform compatible with it. In other words, we want a transform that respects the alpha scale and also takes into account the beta deformation of the function. This is the main idea behind the construction, but if we want this transform to be useful for differential equations of higher order, we also need a consistent notion of higher order fractal derivatives. So the goal is not only to define a new integral transform. The goal is to build an operational framework, a compatible transform, suitable derivative rules, and formulas that can be used to solve fractal type differential equations. The next step is to define derivatives of higher order. The first order derivative is the starting point. But to go beyond first order, there is an important choice to make. A first possible idea would be to obtain the second order derivative by applying the same beta alpha operator once again. This option is discarded because it repeats the nonlinear beta deformation at every step. That would make the iteration harder to interpret since each new order would introduce another nonlinear reshaping of the previous one. The definition on the right follows a more natural idea. The beta deformation is introduced only once at the first step. After that, we continue differentiating with respect to the alpha scale. This diagram summarizes the construction. We start with f. The first arrow gives the first beta-alpha derivative. Then each following arrow applies the alpha scale derivative. In this way, the higher order structure is built by repeated alpha scale differentiation without adding a new nonlinear deformation at each step. This gives a consistent hierarchy of higher order fractal derivatives. And when alpha and beta are both equal to 1, the construction reduces to the classical derivative of order n. The construction of the transform starts with the choice of the kernel. Since the derivative acts on the alpha scale, the integration must also be written on that scale. This is why the measure is d of t raised to alpha. The kernel is chosen for the same reason. The exponential shown here has the key property we need. When it is differentiated with respect to the alpha scale, the result is simply multiplication by minus s. This is the analog of the classical Laplace kernel, but adapted to the alpha scale. The next identity shows that the same idea is compatible with the beta-alpha derivative. The beta deformation changes the exponent and produces the corresponding multiplicative factor. So the kernel is not arbitrary. It is selected because it interacts correctly with the derivative. This leads to the definition of the alpha Laplace transform. In this definition, there are two essential elements. The kernel depends on t raised to alpha, and the integration is performed with respect to d of t raised to alpha. Together, these two choices make the transform compatible with the alpha scale. This is the first operational result. Under suitable regularity and convergence assumptions, the alpha Laplace transform of the beta-alpha derivative has a clean expression. The derivative is transformed into two terms. The first term contains the transform parameter s multiplied by the alpha Laplace transform of f raised to beta. The second term is the initial value, also raised to beta, so the formula keeps the same structure as the classical Laplace rule, but the function inside the transform reflects the beta deformation. This is the first sign that the new transform is compatible with the fractal derivative. Let us briefly see why this rule holds. We start with a truncated version of the transform, where the upper limit is r instead of infinity. The highlighted term is the fractal derivative. Using the definition, this term can be rewritten as an alpha scale derivative of f raised to beta. This is the key simplification. At this point, we apply integration by parts on the alpha scale. After integration by parts, two contributions appear. The first one is a boundary contribution. The second one is an integral involving f raised to beta. Next, the boundary contribution is expanded. It gives one term at r and one term at 0. Under the convergence assumptions, the term at r vanishes as r goes to infinity. The term at 0 remains, and it becomes the initial value contribution. Finally, the remaining integral becomes the alpha Laplace transform of f raised to beta. This gives exactly the first order operational rule. By iterating the first order rule, we obtain the corresponding formula for higher order derivatives. The structure is very similar to the classical Laplace transform rule. The leading term contains the power s to the order n, multiplied by the alpha Laplace transform of f raised to beta. Then the remaining terms contain the initial data. The first initial term comes from f at 0 raised to beta. The rest of the sum contains the lower order fractal derivatives evaluated at 0. So the formula has the same operational meaning as in the classical case. A higher order derivative is transformed into an algebraic expression involving powers of s and initial values. The difference is that the transformed function is f raised to beta, and the derivatives are the higher order beta-alpha fractal derivatives defined before. Besides the operational rules, the alpha Laplace transform also has the expected structural properties. First, the transform is linear just as in the classical case. Second, under suitable admissibility assumptions, the integral converges absolutely in a half-plane and uniformly on smaller half-planes. Third, in the same region, the transform defines an analytic function of the complex variable s. These properties are important because they show that the construction is not only formal, it is a well-behaved transform with the same basic analytic structure as the classical Laplace transform. The transform also has other operational rules. These play the same role as in the classical Laplace transform. A scaling in the original variable produces a rescaling of the transform parameter. A translation in the alpha scale becomes an exponential factor. The third rule is especially important for the application later. Multiplication by powers of t raised to alpha becomes differentiation with respect to the transform variable s. Finally, the transform also has a periodicity rule, again written with respect to the alpha scale. Together, these identities give us a practical calculus for working with the transform. As an application, consider steady radial heat conduction in a long cylinder. Because the cylinder is long and the situation is radially symmetric, the temperature can be described using only the radial distance from the center. The cylinder has an outer radius, and the quantity we want to describe is the temperature profile from the center toward the boundary. This is the classical stationary model. It combines the radial diffusion term with the internal heat generation term, represented by Q sub G over K. Here, Q sub G measures the heat generated inside the material, and K represents the thermal conductivity. The goal is to predict how the temperature changes as we move from the center of the cylinder to the outer boundary. In the fractal version, the same physical idea is kept, but the radial operator is written on the alpha scale and the temperature response is modified through beta. So alpha changes the way radial distance is measured, while beta introduces a nonlinear response in the temperature variable. This gives a fractal stationary radial model for the same heat conduction problem. Starting from the fractal radial equation, we rewrite the model in terms of the first and second order fractal derivatives. The source term, coming from internal heat generation, remains on the right-hand side. Next, we apply the alpha Laplace transform. To simplify the notation, we introduce y of s as the alpha Laplace transform of the temperature raised to beta. Using the higher order rule, the fractal differential equation becomes an ordinary differential equation in the transform variable s. At this point, the problem is no longer written in the radial variable. It has been transferred to the transform side. Then we solve this transformed equation for y of s. The solution contains one integration constant together with the term produced by the heat generation. After that, we apply the inverse alpha Laplace transform. This takes us back from the transform variable to the radial temperature profile. Finally, using the boundary temperature at the outer surface, the integration constant is determined. The result is the explicit temperature profile shown here. This formula describes how the temperature changes from the center of the cylinder to the outer boundary under the fractal radial model. The final formula can also be visualized. On the left, the color profile represents the temperature inside the cross-section of the cylinder. On the right, the graph shows the normalized temperature from the center to the outer boundary. The sliders control the parameters alpha and beta. As these parameters change, the shape of the temperature profile also changes. Alpha modifies the radial scale, while beta modifies the nonlinear temperature response. This shows how the fractal model changes the distribution of heat inside the cylinder. Let me finish with three main conclusions. First, we constructed a Laplace type transform adapted to the fractal scale. Second, we obtained first order and higher order operational rules for the beta alpha derivative. Third, these rules provide a method for solving fractal type differential equations, as shown in the radial heat conduction example. Overall, the construction preserves the spirit of the classical Laplace transform but extends it to a setting where the derivative and the integration are written on a fractal scale. Thank you very much for your attention.